On September 15, 2011, the Kepler science team published a paper in the journal Science, confirming what science fiction had imagined for decades: a planet orbiting two stars simultaneously. Kepler-16b, a planet roughly the size of Saturn, circling a pair of stars in the constellation Cygnus, its existence revealed by two distinct dips in the star's combined light as the planet crossed first one, then the other. The press coverage reached immediately for the obvious reference: Tatooine is real. The universe contains worlds with two suns. George Lucas, it turned out, had been describing something that actually exists. The same paper contained an orbital model. That model showed Kepler-16b's distance from each individual star varying by tens of millions of kilometers across a single cycle of the binary's mutual orbit. The thermal consequence of that variation for a hypothetical surface received no discussion in the main text. The word Tatooine appeared in dozens of headlines that week. The distance variation did not. A planet in a binary star system does not orbit a fixed gravitational center with a predictable distance to its heat source. It navigates two independently moving stars whose combined gravitational influence shifts its orbit continuously, varying the energy it receives by factors that drive the surface between global melt and global freeze on timescales with no fixed period and no pattern that evolution or civilization can anticipate. Kepler-16b is too cold for liquid water. The press releases noted this carefully, but the discovery confirmed that circumbinary planets exist, that their orbits can be dynamically stable on long timescales, and that the universe does not restrict worlds with two suns to science fiction. What the discovery framing did not examine is what dynamically stable means for the climate of a planet whose two heat sources are moving relative to it, and whether orbital stability and climate stability describe the same condition. They do not. To understand why, start with the single star case, not because it is the universe's standard, but because it is the comparison that reveals what changes when a second star is added. A planet orbiting one star follows an ellipse. The ellipse is not perfectly circular, which means the planet is sometimes slightly closer to the Sun and sometimes slightly farther, varying its heating by a moderate amount over each orbit. Earth's orbit is nearly circular, and the variation in solar energy we receive from our closest approach to the Sun versus our farthest is about 3%. Mars's more elliptical orbit produces a variation of about 40%, which contributes to its severe dust storm season. These variations are predictable, regular, and bounded. The same ellipse repeated annually, deviating from year to year only by tiny gravitational nudges from the other planets that accumulate over millions of years. A planet orbiting two stars is not a two-body problem with an extra light source. It is a three-body problem, and the three-body problem is one of the oldest unsolved problems in classical mechanics. In 1890, Henri Poincaré demonstrated that the gravitational interaction of three massive objects moving under each other's attraction has no general closed-form solution, meaning there is no equation you can write down that gives you the position of all three bodies at any future time, the way the two-body equation does. You can calculate it numerically, stepping forward in time in small increments and computing the forces at each step. But numerical integration accumulates errors, and more importantly, the underlying system itself is sensitive to initial conditions in the mathematical sense. A difference in starting position that is smaller than any measurement can detect compounds into a completely different trajectory over long enough time. This is not a computational limitation. It is a property of the physics. A planet in a binary star system is not in a stable ellipse. It is in a path that shifts. The shift happens on multiple timescales simultaneously. On the timescale of the binary star's mutual orbit, which can be days for tightly bound pairs or years for widely separated ones, the planet's distance to each individual star varies continuously as the stars revolve around their common massive center. When both stars happen to be on the near side of their mutual orbit simultaneously, the planet is closest to both heat sources at once. When one or both have moved to the far side, the planet's heating drops. The total stellar energy arriving at the planet, the number that determines whether its surface is liquid, frozen, or molten, oscillates with the binary's orbital period in a pattern that is not the same as the planet's own orbital period, producing a beat frequency between two independent cycles. Over longer timescales, centuries, millennia, millions of years, the three-body perturbation shifts the planet's own orbital shape. The orbit that appears nearly circular today may become more elliptical under accumulated gravitational nudges, moving the planet's average distance from the stellar system. The eccentricity variation that produces Mars's dust storms operates on Earth's orbit on roughly 100,000-year timescales and is one of the drivers of ice age cycles. In a binary system, the equivalent variation operates on shorter timescales and at larger amplitudes because the perturbing force is not a distant Jupiter-mass planet, but a second star at close range. The result is a planet whose effective heating varies by factors that have no equivalent in the single-star habitable zone. Run the numbers on a typical circumbinary planet in what the orbital stability literature calls a stable configuration. Both stars combined are roughly one solar mass. The stars orbit each other with a period of 40 days at a separation of about a fifth of the Earth-Sun distance. The planet orbits both from a distance that places it near the combined habitable zone. During the phase of the binary cycle when both stars are aligned on the near side of their mutual orbit, the planet receives roughly 30% more energy than when the same stars are on the far side. 30% is the difference between Earth's current climate and a significantly warmer world. Applied at irregular intervals with no fixed periodicity and superimposed on the planet's own orbital variation, 30% is the input driving two feedback systems that the planet's own atmosphere amplifies in both directions. When the heating increases, the surface warms. As the surface warms, ice retreats. As ice retreats, the surface absorbs more energy instead of reflecting it, which warms it further. This is the ice albedo feedback, the same mechanism that operates on Earth during ice age cycles and that glaciologists study in cores drilled from Greenland. On Earth, this feedback is bounded by the astronomical forcing that drives it. The Milankovitch cycles are slow, regular, and modest in amplitude, and the feedback amplifies a predictable input into a manageable output. On a binary star planet, the forcing is neither slow, regular, nor modest. The feedback amplifies an irregular, high-amplitude input. The warming does not stop at a new equilibrium defined by the forcing. It stops when the ice is gone and the ocean is hot. Then the stars move. When the heating decreases as the binary moves into the far side phase of its mutual orbit, the surface cools. As the surface cools, water vapor in the atmosphere condenses and precipitates, releasing latent heat briefly before the planet's energy budget falls below the threshold needed to maintain liquid surface water. Snow accumulates at high latitudes. Ice reflects energy, cooling the surface faster. The feedback that amplified the warming now amplifies the cooling, and the planet that was hot enough to boil shallow seas begins the march toward a fully glaciated state at a rate that has no counterpart in the geological record of any single star world. Both of these feedbacks operate on timescales shorter than evolutionary adaptation. In 2011, the same year Kepler-16b was announced, a separate team published numerical simulations of climate evolution on hypothetical Earth-like planets in circumbinary orbits around systems similar to Kepler-16. The simulations ran for the equivalent of several binary orbital periods and tracked surface temperature, ice cover fraction, and atmospheric water vapor. The results were not uniform catastrophe. Some configurations produced stable mean temperatures within the liquid water range, but the temperature variation within those stable mean configurations spanned ranges of 30, 40, and in some cases more than 60 degrees Celsius over a single binary cycle. 60 degrees Celsius of variation over a period shorter than a century is not a climate oscillation that complex land life as we understand it survives intact. It is sterilization of surface environments, repeated on a schedule defined by orbital mechanics rather than by anything the biosphere can influence. The specific configuration matters. A binary pair with nearly identical stellar masses on nearly circular mutual orbits with a planet in a distant low-eccentricity circumbinary orbit produces the minimum possible flux variation. In this optimal geometry, the individual stars' positions matter less because they are similar in brightness, and their distance variations partially cancel. The Kepler catalog contains a handful of candidates that approach this configuration. They represent a narrow slice of the binary system parameter space the telescope surveyed. The fraction of binary systems that does not approach this configuration is the remainder. Roughly half of all stars in the galaxy are in binary or multiple star systems. The universe's most common stellar environment is a multiple star environment, which means the question of binary star habitability is not a question about an exotic edge case. It is a question about whether the most common type of stellar neighborhood in the galaxy can produce the climate conditions that complex life requires. And the three body dynamics that govern planetary orbits in those neighborhoods provide a precise, physics-based answer that does not depend on which specific system is examined. The answer is that dynamical orbital stability and climate stability are not the same condition, and the binary configurations that produce the most dramatic skies are the configurations where the gap between those two conditions is widest. The close binary pairs, two stars near enough to each other to produce distinct double shadows, brilliant overlapping light, the double sunset that the concept artists reproduce, are exactly the configurations where the gravitational interaction between the stars is strongest, the perturbation on the planet's orbit is largest, and the flux variation per binary cycle is most extreme. Kepler-16b's two stars are separated by about a fifth of the Earth-Sun distance. They are close enough to each other that a viewer on a hypothetical warm version of the planet would see both as individually distinct disks in the sky, the smaller one noticeably dimmer, but clearly present as a separate source. That closeness, the visual feature that produces the beautiful sky, is also the feature that makes the gravitational interaction between the stars strong enough to perturb the planet's orbit significantly over short timescales. The double sunset is the visible signature of the mechanism. The obvious candidate for a civilization surviving this environment is to go underground. Remove the habitat from direct exposure to the surface temperature variation, insulate against the climate swings, and operate from a stable subsurface thermal environment that changes slowly regardless of what the stellar flux is doing above. This works, within limits, for temperature variation on moderate timescales. The thermal diffusivity of rock means that surface temperature fluctuations take time to propagate downward, and deep enough underground, the temperature stabilizes near the planet's geothermal baseline. It does not work for climate variation that drives the atmosphere itself between composition-altering extremes. A fully glaciated surface, with ice extending to the equator and the atmospheric water vapor content near zero, changes the atmospheric pressure, the photochemical reactions on the surface of the ice, and the subsurface thermal gradient. A surface that has been at boiling ocean temperatures for decades before returning to below freezing conditions has lost water to space through atmospheric escape during the hot phase, water that does not return when the cooling begins, incrementally draining the planet's volatile inventory each cycle. The subsurface habitat that survives one climate cycle emerges into a different surface environment than it entered. After enough cycles, the environment on the surface is not the one the biology that built the underground habitat was adapted to, and the materials and energy sources required to maintain the habitat may no longer be accessible from below. Kepler's successor missions have continued cataloging circumbinary planets. TESS, the Transiting Exoplanet Survey Satellite, has added to the list. The systems confirmed include a range of stellar mass ratios, orbital separations, and planetary distances, and the orbital stability analyses published for each confirm the same basic result. The orbits are stable on million-year timescales. The climate analyses are rarer, more recent, and more qualified. The language in the climate papers is precise in a way the discovery announcements are not. Flux variation factors, temperature excursion ranges, feedback amplification estimates, all carefully bounded by the assumption sets of the models used. The assumption sets always include a note about the three-body perturbation on longer timescales, the orbital eccentricity variation that the models cannot run long enough to fully capture, because running a climate model for 10 million years at sufficient resolution to track the feedback dynamics requires computational resources that do not yet exist, and because the orbital element drift that feeds the climate model's boundary conditions is itself uncertain on those timescales, due to the sensitivity to initial conditions that Poincaré identified in 1890. The chaos is not in the simulation, it is in the physics the simulation is trying to describe. No confirmed detection of complex life exists on any planet in any stellar system. The baseline for comparison is a single data point, Earth, one sun, a nearly circular orbit, and 4 billion years of climate variation bounded enough for unbroken biological continuity from single cells to civilizations. The binary star planets that the Kepler and TESS missions have confirmed are real worlds with real orbits and real stellar flux environments, and none of them has been shown to host biology of any kind. The absence of data is not evidence of absence in the strong sense. The surveys are not sensitive enough to detect biology at the level it might exist. But the physical conditions those worlds experience, modeled from their confirmed orbital parameters, are not conditions that the one example of complex life in the known universe developed under, or conditions that the physics of climate feedbacks suggests it could have. What the planetary habitability research community has not yet answered, and what the growing catalog of confirmed circumbinary planets makes increasingly urgent to address, is whether the orbital stability criteria currently used to classify binary star candidates as potentially habitable account for the full range of flux variation those planets experience over geological timescales, or whether they identify the minimum condition for orbital retention while leaving the maximum condition for surface sterilization unexamined. Because a planet that stays in its orbit for 1 billion years while its surface cycles between ocean and glacier every few centuries has achieved one kind of stability and failed at the other, and the kind that matters for life is not the kind that the stability papers are measuring.